So my name is Ilya Yakovlev. I work at Borskov Institute of Catalysis in Novosibirsk, and I also participate in a joint PhD study between Novosibirsk State University and ESPCI in Paris under the supervision of Jean-Baptiste Despinoz and Olga Lapina. The topic of my report today is the application of cobalt-59 internal field NMR for determination of size and structure of cobalt nanoparticles. Cobalt-59 internal field NMR, or some call it zero field NMR, is a well-known powerful technique that allows studying various properties of various structural properties of ferromagnetic materials based on cobalt. For example, this technique can provide information on molecular structure of the study sample. In metallic cobalt, for example, it can discern between FCC, HCP, and BCC structures. It can also provide information about the magnetic structure of particles, because they can be either single or multi-domain. It can also provide data on particle size distribution indirectly, but through the so-called superparamagnetic transitions. And also it can be used in studying alloys and interfaces of cobalt with other metals. Many different types of materials can be studied using this technique. It may be bulk cobalt or 2D layered structures, cobalt nanowires, or 1D structures. And but we are particularly interested in zero-dimensional particles, or just cobalt nanoparticles. Cobalt nanoparticles can find a lot of different applications. Some of the important ones are, of course, heterogeneous catalysis. The important examples of cobalt catalysts are catalysts for Fischer-Tropsch synthesis or water-gas shift reaction. They can also be used in different electromagnetic shielding materials with tunable absorption, reflection, and transmission of electromagnetic waves. And such materials can be applied as coatings of different thickness. And of course, there are many more applications for cobalt nanoparticles. So the main aim of our work was to apply internal field NMR on cobalt-59 nuclei for characterization of size, distribution, and molecular structure of, in this case, hybrid materials composed of cobalt nanoparticles embedded inside multi-volt carbon nanotubes, and for studying Fischer-Tropsch catalysts of cobalt represented by cobalt nanoparticles supported on metastable alumina phases. So first of all, let's talk about size distribution studies. And the important physical phenomenon here is the superparamagnetism. The NMR response of cobalt nanoparticles greatly depends on their size. And in case of relatively big particles, larger than roughly 10 nanometers, these particles are ferromagnetic, generally, at room temperature. They can be either multi-domain or single domain, and they produce a normal internal field NMR signal. But if we decrease the size of the particles below 10 nanometers, it may happen that the energy of magnetic anisotropy of the particle becomes lower than the thermal energy of the our media. So this could result in thermal flips of magnetization during the time of experiment. And if the thermal flips of magnetization happen frequently enough, the NMR signal from such particles is completely lost from the spectrum. Such particles are called superparamagnetic. And of course, in order to undergo this transition from ferromagnetic to superparamagnetic state, we can either decrease the size of the particles or increase the temperature, because such increase the thermal energy and the frequency of thermal flips. The behavior of such particles is governed by the Néel equation, which is basically an Arrhenius type equation for thermal flips of magnetization. So in order to study this phenomenon, we have obtained what we consider a perfect candidate for such an experiment, because it was cobalt nanoparticles embedded inside small carbon nanotubes and at very low cobalt concentration. So according to TEM data, all the cobalt nanoparticles in the sample were located inside the carbon nanotubes, and thus they were limited in size to roughly 4 or 5 nanometers by the walls of the carbon nanotubes, which resulted in a relatively narrow size distribution of cobalt particles, and the size of these particles was quite small. And so we have recorded the internal field NMR spectra of this sample at the room temperature, the black spectrum, and at 30 Kelvin. And we have observed a more than 40-fold increase of integral intensity of the spectrum when we went down to 30 Kelvin. And please take note that all of the necessary corrections for Boltzmann factor, Curie-Weiss factor, and T2 relaxation constant were already made for this spectra. So the 40-fold increase of intensity is could only be caused by additional cobalt particles that were blocked into ferromagnetic state from superferromagnetic state during this transition. So and then we compared the observed intensity increase with the theoretical prediction that could be made from the Néel formula and applied to the particle size, or better to say particle volume distribution obtained by TEM. And we found a very good agreement with the good agreement of the experimental data and the calculations about how big was the volume of the particles that were blocked when we went down to 30 Kelvin. But of course, to apply this formula, we need to know the so-called thermal flip constant, which is an unknown value in this Néel equation. And to do this, we used some additional ferromagnetic resonance experiments. In the ferromagnetic resonance spectra, we have observed a very complex signal, but we could distinguish two different lines at around 3000 Ørsted. The very broad line corresponding to ferromagnetic particles, single domain particles, so particles in a block state, and a very narrow line located at the same frequency, but corresponding to superferromagnetic particles. And contrary to NMR, in FMR, we can observe the superferromagnetic particles, and even more, they produce a very sharp intensive signal, because, well, they are ferromagnetic, and this is basically a EPR applied to ferromagnetic materials. So from these quantitative measurements, we have extracted the value of tau zero, the thermal flip rate constant, and then we were able to apply it to the Néel formula. So that was about the particle size distributions. And as for particle structure studies, first we used a sample of the same type, cobalt nanoparticles located inside, or this time maybe outside carbon nanotubes, but with a larger cobalt concentration, because such samples are practically interesting. And in this case, this sample was a catalyst for ethylene polymerization. This process then, if we polymerize ethylene on such a catalyst, we then obtain a material that is basically ethylene with cobalt nanoparticles and carbon nanotubes embedded in its volume. And such materials can have interesting electromagnetic properties such as absorption and reflection. And it is generally considered that the cobalt nanoparticles retain their size during the polymerization ethylene. But this is really hard to prove using such techniques as TEM or XRD because of the very large signal from polyethylene in XRD, or because the experiment of the TEM experiments with the polyethylene materials are really hard to execute. So we have recorded the some spectra for the initial basically composites of cobalt and carbon nanotubes before polymerization of ethylene, but unfortunately at lower concentrations than they studied later. And we have observed that at concentrations above 10% of 10 weight percent of cobalt, we saw an appearance of many different lines corresponding to FCC single domain cobalt particles, HCP cobalt, and even domain walls from HCP cobalt. So this basically signifies the presence of signal in this area signifies that the particles are relatively big. But in a sample with a really huge concentration of cobalt of 34%, we saw a line shape in NMR spectrum that was really much like the line shape for the spectrum of sample before polymerization with the lowest concentration of cobalt. And thus we can say, we can suppose that during the polymerization process, the particles of cobalt actually break down to smaller particles and thus produce such characteristic signal for small cobalt particles. And the second object of our study were Fischer-Tropsch synthesis catalysts supported on metastable aluminas. It is there is a vast amount of scientific information about the activity of cobalt particles in this process, and it is considered that relatively large particles with the size between 10 to 20 nanometers and that have HCP symmetry, HCP structure, are the most active and selective in this process. And so it is really interesting to understand if we can control the formation of cobalt particles by choosing different types of support that we use. So metastable alumina phases are the very frequently used supports for heterogeneous catalysts, and we have chosen two very different metastable phases, K alumina and gamma alumina, which had comparable specific surfaces, but that are very different in the dominating plane on the surface, because for K alumina, the most prominent plane is 111, and for gamma alumina, it's the 110 plane. And recently, Chezalet et al. And others from France have shown that the initial stage of interaction between cobalt precursor and the hydroxyl coverage of the support, in that case it was alpha alumina, plays the crucial role in the formation of cobalt particles later during the reduction. And from the models that we used in the article of Chezalet and the models that we used earlier to predict the chemical shifts of different types of metastable aluminas, we see that the surface of K alumina represents the C mu2 plane of alpha alumina, and the 110 plane, or which is dominant for gamma alumina, looks like the C mu1 mu2 plane. And they're different in that in this case, for gamma alumina and C mu1 mu2 plane, we have also we have a mixture of terminal hydroxyl groups and bridging hydroxyl groups. And according to the energetic calculations made in this article, this really facilitates the interaction of cobalt precursor with the surface of the support, which would in turn lead to a stronger dispersion of cobalt over the surface of the support. And in our theory, this would then lead, to formation of smaller cobalt particles, which we actually do not want. We want to formation of cobalt nanoparticles which are above 10 nanometers in size. So we have, prepared different samples.
Excuse me, Ilya, you have only 2 minutes else.
Yeah, of course. It's my last slide. Yeah, we have prepared cobalt Fischer-Tropsch catalyst with different cobalt concentrations on supporting K alumina and gamma alumina, and from the internal field NMR spectra recorded at 30 Kelvin, we have observed a significant difference of these samples in the area that usually corresponds to HCP phase. And the most drastic difference, of course, is for the lowest concentration of cobalt. This difference may mean that the particles supported in gamma alumina are actually smaller, because it is generally considered that the FCC structure of cobalt is stable for smaller particles, and HCP becomes stable for larger particles. So here the internal field NMR provides evidence that the particles on gamma alumina are actually smaller. But it may not be the only reason for the such difference in HCP cobalt presence on the support, because the surface of the key alumina of the 111 plane of the spinel structure has actually a very nice hexagonal symmetry, and we think it maybe even promotes the formation of hexagonal phase of metallic cobalt. This was also observed in TEM experiment. The structure of key alumina had a very strict hexagonal symmetry. So yes, let's switch to the conclusions. So basically, we have observed supermagnetic state. We have observed supermagnetic transitions in the samples of cobalt on carbon nanotubes. We also can propose the theory that larger cobalt particles break down to smaller parts for cobalt carbon nanotube composites with high concentrations of cobalt. And it seems that key alumina may be a promising support for Fischer-Tropsch synthesis due to its weaker interaction with cobalt precursor. So thank you for your attention. I hope we still have some time for questions.
Okay. I think we have time for only for one question. Is it? Can you ask? Maybe. Okay.
Maybe.
Please, Professor Chizhik.
Please, Ilya, show me, please, slide number 11. Yes. I have missed which equipment did you use for measurements?
It was, yeah, it happened so that we used many different equipments. So some I didn't have time to point it out here.
For example, for left.
The spectra from the left, they're actually from the article by Andreev from our group. He was in our group. I think these measurements were done in Yekaterinburg in Mikheyev Institute.
But which method was used for the obtaining each point? Free induction, decay, or spin echo, or other?
Oh, it was a pretty usual technique. It's a step-by-step spin echo experiment with the change of carrier frequency. To obtain the intensity, then the echo signal was Fourier transformed, phased to
what pulse sections?
Sorry?
What was pulse sequence? Pulse sequence.
Последовательность какая использовалась? Импульсная.
It's a solid echo. It was a 1 microsecond pulse, then 8 microsecond delay, and then again 1 microsecond pulse. So we didn't measure what angle is this. So yeah,
Thank you. But magnetically ordered substances, there is so-called amplification factor, which produced strong signals. Which amplification factor for these samples?
we did not measure the amplification factor, but these spectra are corrected for it by the technique when we record spectra with different powers. So it's basically a 2D spectrum with different, with one axis is the frequency, and the second axis is the pulse power, radio frequency power, and these spectra are corrected for enhancement coefficient.
I think you cannot.
Yeah, certainly. Okay, Professor Chizhik, can we finish this part of our schedule, because we have a time? We have to introduce the next report.
Yes.
Okay. Okay. Thank you very much.